And welcome to Calculus 2. We're going to see how much we can finish of our discussion of first-order linear differential equations. We already saw how to solve them. We're going to go about finding this integrating factor, and then we're going to build the solution. So let's start us off with a problem. This is section 9.2, problem number 8. It's from page 548 to 550. We're going to solve this differential equation. So let's see here. It is linear because we have the derivative right here. That's our dy dx. We have our function with the y, and we have a function just by itself. Now note, this is not quite in linear form quite yet, because write this out, e to the 2xy 2x. There's not supposed to be anything multiplied by the dy dx. Remember, it's supposed to be dy dx plus p of x times y equals q of x. So we've got to divide by what's on the dy dx, so we divide everything by e to the 2x. E to the 2x. That's just going to get us, let's see, here just 2y, there 2x e to the negative 2x, and then here dy dx. Alright then, we need to find our integrating factor. Our integrating factor came out to be e to the integral of p dx. In this case, p is just 2. So e to the integral of 2 dx, that will be e to the 2x. Alright, that's our integrating factor. So our solution is going to be y equals 1 over v of x, integral of q of x, v of x, dx. So we're just going to get 1 over e to the 2x, integral q of x, which is 2x. I guess I wrote this version for some reason. I might as well stick to it, but 2x e to the negative 2x is what I had. So 2x over e to the 2x times, well, e to the 2x dx. So that goes away, and we're just integrating 2x, so that is going to just be x squared. So we'll get x squared over e to the 2. Oh, so not do that yet. 1 over e to the 2x times x squared plus c. Now note, the c is going to be multiplied by this. So I'm not just going to have a c out by itself in this one. But that's good enough for this. I think that's good enough for a solution. 1 over e to the 2x, x squared plus c. Let's do another example. This is problem 12. Once again, we have a coefficient on our derivative term that we need to divide out. So if I do that, everything divided by t plus 1. That's going to get us ds dt plus 2 over t plus 1 s equals 3 plus 1 over t plus 1 cubed. So here we have our q of t on this side, our p of t, and our derivative. So we make our integrating factor, our v of t, e to the integral of p of x dx, or p of t, I guess. So e to the integral of 2 over t plus 1 dt. So that's e to the ln well, I guess I get 2 ln of t plus 1. And then you can take that 2 into the exponent, e to the ln of t plus 1 squared, and then that just becomes t plus 1 squared. So then, our s of t is 1 over that, so 1 over t plus 1 squared, times integral of q of t, so all of this, 3 plus 1 over t plus 1 cubed, times t plus 1 squared dt. Multiply that through, we've got 3 times t plus 1 squared plus t plus 1? Oh, 1 over t plus 1. 1 over t plus 1. So we're integrating that. Still got to multiply that when we're done, but integral of 1 over t plus 1 is ln of absolute value of t plus 1. Integral of t plus 1, since derivative of the inside is just 1, it's just be like integrating t, so t squared, increase by 1, divide by it, so t plus 1 cubed divided by 3 gets rid of that, so t plus 1 cubed plus c times 1 over t plus 1 squared and honestly that's fine as a solution. Try to solve this one yourself. Just pause it and give it a shot. This one's got an initial value problem, so we will actually have to find the c at the end. But other than that, I don't think it'd be too bad. Let's see, divide out the theta, dy d theta, minus 2 over theta y equals theta squared, secant theta, secant theta, not secant squared, tangent theta. The theta greater than 0 is just a statement about its domain. Alright then. Here's our p. So, integrating factor v of theta will be e to the integral of negative 2 over theta d theta. So that's e to the negative 2 ln of theta. Take the 2 up into the exponent, that's e to the ln of theta to the negative 2. So that's 1 over theta squared. Our y of theta is 1 over theta squared. So just theta squared. Integral of all of this stuff, theta squared, secant theta, tangent theta, times v, so that would be 1 over theta squared d theta. So theta squareds go away. Oh, and that makes it a really easy integral. Integral of secant tangent is just secant, yeah, secant. So this becomes theta squared secant theta plus c. And we know when y of pi over 3, so when theta is pi over 3, we have pi over 3 squared secant of pi over 3 plus c equals 2. Guess I might as well just divide this, multiply this over, so pi squared over 9, so multiply it over, you get 9 times 2 is 18 over pi squared. Secant of pi over 3. Cosine of pi over 3 would be 1/2. So secant would be 2. So 2 plus c equals 18 over pi squared. So c 18 over pi squared minus 2, which I guess would be 18 minus 2 pi squared. Yeah, 18 minus 2 pi squared over pi squared. So then, y of theta, our specific answer, is going to be theta squared times secant theta plus 18 minus 2 pi squared over pi squared. There we go. Next time we'll go on to the next section and we'll talk about applications of differential equations and specifically linear differential equations. After that we'll start looking at, I believe, phase planes and phase lines, which is some neat stuff. Look at a lot of different kinds of applications in the next section. I think 3 main classes, but they all have their interest. See you then. Have a great day.